here in just a moment. We'll introduce ourselves. I'm Tyler Metzger. I'm one of your tech leads.
My name is Raymond Yu, and I'm also a tech lead for DSC at UF.
I'm Sindhu. I'm also a tech lead at DSC UF.
So today we'll be going over a workshop on machine learning and introduce you to some of the models typically used in machine learning. We'll first go over an overview of like machine learning and the typical fields that are associated with it, such as maybe big data, artificial intelligence. Then we'll move on to some just brief models like linear regression, logistic regression, convolutional neural networks. And then finally, the other tech lead, Tyler, will do a demo on how you can use some of these models that we discussed in order to identify handwritten digits. So first off, problem framing. So before you do machine learning, you have to sort of figure out how to frame your problem, and it's best to break it down into pieces. You have to consider the input data you have. You have to see if it's numerical, like maybe 24, 100, or whatnot, like different values, or is it categorical, like classes? So you have to identify whether data is like, it says alive or dead, red, blue, green, stuff like that. And additionally, if it happens to be numerical, you have to be consider whether it is discrete or continuous. And discrete would just be like 1, 2, 3, and then continuous would just be like 23.53, or maybe an irrational number approximation. One final thing to consider for your input data is whether the numbers have meaning, because sometimes in your input data, you may have like ID numbers, which inherently you do not want really to feed into your model because the meaning is very arbitrary. So second, you have to figure out what type of output data are you expecting. So do you want labels, or do you want probabilities of certain events happening? Some models are better at doing like certain objectives. So knowing these whatever algorithm you choose can help you choose whatever model you decide to use. And some other questions would be like, how big is your data set? So maybe you have to do some big data techniques to help process the data more. Or how computationally expensive is one model versus the other, because you may be limited to whatever PC or computer you are using. And can you adjust your data to better fit the objective and allow it to be more streamlined to the model? And this is what we were discussing in our previous workshop on data cleaning, so we can clean up some of that dirty data. So this is an introduction to machine learning and some of the fields that you may encounter. So first off, what is machine learning? Well, machine learning is the study of algorithms that autonomously improve through experience, and is the process of finding or learning the hidden relationship within that data. This may sound a little scary, and in media, they may call it like the dawn of artificial intelligence or Skynet. However, this learning is not really exactly the same as a human or animal's definition of learning, and it doesn't really go beyond a defined set of instructions. The difference between machine learning and traditional algorithms is the fact that machine learning algorithms, they self-improve without a person having to explicitly make changes. And this gives the appearance that it is learning. In essence, a machine learning algorithm tries to uncover a relationship between sets of data. It builds a model based on sample data and makes a prediction without being explicitly programmed to do so. So, as an example, say you want to classify images, which each image may have thousands of pixels, and these pixels can be red, green, or blue, like different values. Explicitly programming this classification would be a nightmare, because you have to see which pixel is what, and then you can make a different classification. So you let the algorithm find the pattern itself within the images. This leads to an approximation. So typically machine learning algorithms are not usually 100%. However, many strong algorithms can achieve high levels of accuracy and can even outperform people in some tasks. In general, machine learning is heavily inspired by the field of statistics, and some consider it as applied statistics. It is used in a wide variety of daily applications, and you will likely hear it as a buzzword. And some examples are email filtering, self-driving cars, image recognition, and etc. So we're going to do a poll question before we talk about the fields of machine learning. So you guys can use the link or use the barcode. And then the question. If you have any technical issues, let us know and we'll try to resolve it with the poll. So, yeah. So which of the following is not a subset of machine learning? And then we'll go over the results. Well, I think everyone has had time to input their votes, so we can close the poll. And yeah, you guys did a really good job. And artificial intelligence is not a subset of machine learning. It is actually a more overarching category that machine learning can be included under. And this will be described in the next slide. So yeah, this is a graph or maybe triple Venn diagram that shows how machine learning fits between data science, big data, and artificial intelligence. These fields are ultimately intertwined, but it is best to take this graph with like a grain of salt, as each field always involves elements from the other. So an interpretation that you may have is, although you may start in one field, as you go deeper, you may encounter aspects from the other two fields. We will go over the constituents of artificial intelligence later, but for right now, I'm going to describe just the three main overarching areas. So big data. Big data is the field that involves the problem with dealing with data sets that are too large to be processed by traditional measures. It involves three concepts known as volume, variety, and velocity. Data science is a field that involves utilizing algorithms, systems, or processes to extract knowledge from the data sets. And these data sets may or may not be large. It is interdisciplinary and uses concepts from computer science, math, and statistics. Artificial intelligence is the hardest to define of these three fields, and some describe it as like a machine perceiving its environment and taking actions to increase its chances of completing its goals. This kind of sounds like how organisms live, if anyone knows anything about biology. But others may describe it as the ability for a system to correctly interpret external data to complete assigned tasks. But in general, it is the intelligence displayed by machines or machines mimicking to learn or problem solve. So yeah, we're going to do another poll question before the next slide. Just navigate to the link or scan. So in supervised learning, are the data inputs labeled or unlabeled? Maybe I shouldn't show the results so the majority doesn't affect people's votes. All right, I think everyone's had a chance to put in their vote. Close the poll. So supervised learning involves labeled data. It is part of the definition. So unsupervised versus supervised learning. These are the two broad categories of machine learning, and supervised learning involves labeled inputs. Basically, you use the comparison between estimated and true values to calculate the effectiveness of the model, and also acts like as a metric in order for the model to improve. And this is done by checking how much of the estimated values are correctly calculated against the true values. On the other hand, unsupervised learning does not have any labels for the data, and the algorithm is left with no prompt. Instead, it discovers trends on its own. So these trends can help cluster similar data. You can uncover a hidden relationship, or you can even use it to do supervised learning, and extract features that you're going to use. So this is a closer look at the subfields of artificial intelligence and where machine learning lies in that organization. You can see there's like ML, as we've been talking about, natural language processing, speech, vision, and etc. And these may be disciplines that you have heard before. It is important to keep in mind that the branches in this image are just ways to organize the topics in the field. They're not parallel or completely separate. An analogy that can be made is that these do not represent more separate branches, but more of a tangled bush. So they're always like intertwined. So like, for example, deep learning can actually be used to solve issues relating to image recognition. And some people categorize speech all under natural language processing. So in general, everyone has their own interpretation. And it's just a good way of organizing the field. So training and testing. Training and testing is a very key feature of supervised learning. And when you create a machine learning model, you want to be able to generalize and adapt to unseen data. Because if your model only works with the data you do have, you don't really want, it is not able to extrapolate and defeats the purpose of even creating a model. So when you develop your model, you want to split your sample data to a training and test set. To gauge accuracy, like we said earlier, the testing set compares the labels it calculated, that is true with the labels that are output by the model. So when you split data into training and testing, it reduces this overfitting. So as I said before, your model can use all the data you have and be really good, but if you introduce new data, it lowers in accuracy. So this improves generalizability, which is the term to work with unseen data. And now we're going to do poll question 3, and as earlier, you can navigate to the link or scan the book. So which among the following models is not an example of classification? And we'll see the results. All right, it seems that everyone's gotten a chance to vote, so we're going to close. Oh, oops. Well, the answer is linear regression, and we're going to get to that in our slides. So the models. Linear regression is the first algorithm we're going to be talking about, and it is a supervised algorithm. So this is, you may be familiar with it from statistics courses, but you have known input and output values for the data set, and you create a line of best fit to predict future unseen data points. The line is created using a criteria for error, and one example of a criteria is ordinary least squared. It is not classification because when you predict, you actually predict continuous values, as you can see, that are along the y-axis. This is why it's sometimes called predictive analysis, and you just basically use it to predict things against an independent variable. Sometimes to reduce overfitting and bias, you may introduce a regularization term, and this penalizes the line in case you want to keep overfitting to a minimum. So now we're going to talk about logistic regression. It is also a supervised machine learning algorithm, and unlike linear regression, it focuses on the probability of a categorical binary event or class. So it predicts whether the value is going to be alive or dead, win or lose, cat or dog. And it essentially functions by drawing a line in the mapping space that splits the two categories. And this image, the space is 2D, and then it splits the two clusters with a one-dimensional line. However, the mapping space can be higher than 2 dimensions, and this is pretty hard to visualize in a 2D like space and representation. So that's why linear algebra is very key if you want to pursue the theoretical aspect of machine learning. So now we're going to talk about deep learning, which is a subfamily of machine learning. And these use, this field uses artificial neural networks in order to extract the features themselves in the model. So traditionally in like normal machine learning algorithms, you process the inputs to extract the necessary features. However, in deep learning, the feature extraction is done by the deep learning algorithm, and it's called feature learning or representation learning. And this allows them to learn the features as well as make predictions. So for this reason, sometimes the same model can be just adjusted a little bit to solve a different but somewhat similar task. And because of this, it is more computationally expensive than traditional machine learning algorithms. And a single model can have millions of parameters that need to be trained. So when you want to do deep learning, you need a large amount of parallel processing. So this is why a GPU can be super beneficial when you're training a deep learning model. So now we're going to talk about neural networks. So first, a neural network is made of a bunch of different nodes, and you can think of a single node as a neuron that produces a singular output. You take a bunch of nodes to make several layers, and then you combine layers to make the model, as seen right here. So basically, there is an input layer, and then there's an output layer, and many hidden layers in between. The input layer basically takes the raw info from the image or whatever input data you have, but you may have to map it to a different dimension. So in this case, they did it to one dimension for every single pixel. And then the result is labels that can be identified or used for creating, let's say, results. So recognizing the digits between 0 and 9. Basically, these hidden layers progressively extract higher level features from the input. So let's say you have a very large model. The first couple of hidden layers would probably try to find edges or like vertical lines and whatnot. But as you go into the deeper hidden layers, it'll start, let's say, classifying more advanced images, maybe like human faces or like an airplane or whatnot. So yeah, that is neural networks. Now we're going to talk about artificial neural networks. This is the simplest variant of neural networks and is sometimes called feed-forward neural networks because inputs are only processed in the forward direction. It only has input, hidden, and output layers. And the hidden layers process the inputs and the output layers hold the final results. Basically, at each node, the inputs are summed, so all the previous nodes' results are summed and then multiplied by a weight and added by a bias to obtain a result. But this result is then input into an activation function, which are 4 examples shown here. Basically, these activation functions help the model learn nonlinear relationships. And this is basically the powerhouse of the artificial neural networks, and it's what gives neural networks their strength. But one issue with artificial neural networks is that they do not particularly work well with spatial features, as the data has to be just turned into a one-dimensional vector. This is shown in the GIF or GIF of the previous slide. And as you see, you had to turn an image into like a one-dimensional vector in order to be input in the model. So convolutional neural networks were invented to help solve this problem. And some of the and pattern recognition. A variant of neural networks is recurrent neural networks. So in traditional neural networks, each input is independent of each other. But in recurrent neural networks, you add a loopback input for each neuron. So it considers And finally, we have convolutional neural networks. These are the most popular and are used across all different types of fields and are extremely powerful in the analysis of images or videos. The hidden layers can be made up of convolutional layers, pooling, fully connected, and normalization layers. And they utilize what's called a kernel or a filter in order to capture relevant features or data. This is how it manages to engineer the features. And basically, it maps over a different area of pixels throughout the whole image in order to create what's called a convolution. And since it engineers the features that it uses, this is why it's categorized as deep learning. This also is why it is able to identify spatial features and why it's so powerful when dealing with visual data, and is used in facial recognition, computer vision, and medical diagnosis. So now that I've introduce you to some of the fields of machine learning and some of the models, I will turn over to the other tech lead, Tyler, who will go over how you can use it to identify handwritten images.
All right, thank you very much, Raymond. I'll share my screen here in just a sec. All right, I was voting alongside everyone in the polls. All right, so before we get started, you can actually follow alongside of me if you want to see the GitHub, or after we're done, you can join along. Another lead should be posting the GitHub repo in the chat. So just to go into it real quick, let me move the Zoom stuff. It's kind of blocking some of the view. There we go. Before we get into it real quick, I'm going to be using scikit-learn, which is a Python machine learning library. For those of you that have heard of TensorFlow, this is a lot higher level version of that, essentially, because TensorFlow, you build the algorithms yourself, stuff like that. It can be kind of complex for first time. Scikit-learn is really good for learning machine learning and getting used to some of the concepts, because you get to pick from a lot of different popular models that already exist. So scikit-learn also comes with a few toy data sets. They're called that because they're much smaller than what real world data sets are, which are normally either millions or sometimes even billions of inputs and pieces of data. These toy data sets, and the one I'm going to be using, is about only 1,800 inputs. So to begin, we're going to be doing some imports. The first import is going to be our function load digits, which is going to give us our data set. The next one is a function for us to split into training and testing data. We'll get into that later. NumPy is just for some data processing. And here's some visualization libraries that I'm using. You don't really have to focus on the visualization. If you can't follow along because you don't know matplotlib, there's too much text, don't worry. I'll be going over kind of loosely of what is happening, and you can just see the results. And if you want to play with it on your own, again, it's on the GitHub, and you can always go line by line and see what's happening. So right here, we're going to call load digits. So it's in the digits object. And then we're just going to print some things. Digits.data, that's going to be the actual input data. Each digit, because they're 8x8 images, is actually just a 64 length array with the numbers 0 through 15 to represent the intensity, or like the color of each pixel. Data.target is the label for each pixel, or each image. Sorry, not each pixel, each image. So, digits.data 0 has a label associated with digits.target 0. And then finally, we're just going to print one of the examples. I reshaped it so you can see it is an 8x8. This is what the image is going to look like. But again, remember that it's actually technically just a 64 length array all the way along. But this is actually just the number 0 represented in floats. 0 in this case is going to represent black, with higher number representing lighter pixels. So, the top left is black, next one's black, then it gets maybe dark gray, and then pretty light. And you can see maybe with the numbers, if you see like double digits, you can kind of see that's actually shaping a 0, although that's not the greatest visualization. So right here, what I'm doing is I'm going to use matplotlib to actually show the images. Now, again, you don't have to follow exactly all this code. It's okay if you don't understand it. I'll explain a little bit. This is just giving some figure sizes. This is for drawing some grid lines. So I broke it up into pixels. This is for some subplots. And then we're going to just be showing the images and the labels alongside of it. And I zipped in the images and targets together so it can be treated as an object. But if you run it, again, don't worry about it too much if that got lost there. Totally fine. If you run it, you can see that you'll see the images. This is labeled as 0, 1, 2, 3, 4. I'm sure if you look at it yourself, you can see that. But if you really think about it, how would you know that? I mean, we can recognize it, but that's because we have eyes. How would a computer actually recognize it? So I split it into pixels because and what kind of actual numbers go into recognizing images. As you can see right here, these are the numbers behind it, where each pixel is a number, and it's just visualized here. So as we're going forward, we want to choose our model. We think, what are our inputs? What are our features? Our features are actually just each individual pixel is its own feature. So we have 64 different features in our linear model. Digit is this? How important is the middle one? How important is this one? Et cetera, et cetera. It's going to give each pixel its own weight. And then those weights will have the values that it'll be multiplied by, plus a bias at the end, and it'll give us a target label. Of course, in this case, it's classifying it because, actually, I wasn't supposed to get there just yet, but we are going to be classifying these numbers. I'll explain why in just a sec. So it's going to be splitting it into clusters essentially, rather than actually saying this has a value of 0. But let's start with training and test sets. This is what Ray touched on earlier. We want to split the data into training and testing data. So we put in, our inputs, our labels. This is the split. I'm doing 75-25. It's a little arbitrary. You don't want it to be too extreme in either direction. Again, this is a pretty small data set, so it's going to be pretty sensitive in this case. But usually anywhere from 50-50 to 75-25, maybe even 80-20 is pretty good. In random state 0, when it splits it, it shuffles the data set. I'm putting random state equals 0 here as a seed. So when you guys do this yourself, it'll shuffle it in the same way so you can get consistent results. I'm going to pose a challenge at the end and see if you guys want to try to beat some of the records I'm setting with some of the default models. But just to go over some of these variables, xtrain is our training inputs, xtest is our testing inputs, ytrain is our training labels or training outputs, and ytest is our testing labels or testing outputs. And make sure that we run this. Sometimes I forget to do that with Jupyter. And finally, let's go to choosing a scikit-learn model, kind of the point of this presentation. So when you choose a model, it's one of the most important parts of machine learning, because as good as your algorithms are, if you don't have a good model, I mean, like, what's the point? So you want to make sure that your data is going to fit the model you choose and vice versa. So first, is it supervised or unsupervised? Is the training data labeled? You can just type in chat for it. We'll see different things. In this case, it's supervised because we know the data is labeled. As we saw right here, it has labels, so it's supervised learning. So we're going to be looking at supervised models. Next, what is our input data? What features are we looking out for? Well, I touched on that a little bit earlier, where I say each individual pixel is a feature. In this case, we don't have to edit it too much because the features are just numbers. If it was something like words for like natural language processing, there's different ways you can turn words or images into numbers, but we already explained how this image is actually just numbers behind the scenes. But don't forget that there's a lot of different kind of data you can have, and it's kind of important when you think, how am I going to actually input that in? So what is our output data? Is it numerical or categorical? And I kind of revealed it earlier, but let me just explain myself. So on first glance, you might think it's numerical, of course, because our output's going to be 0, or it's going to be 1 or 2 or 3. But if you think about it, we're just looking at images. Is this image, greater than this image? Is this 2 greater than this image? Of course, 0 is less than 1 is less than 2, but the images themselves don't have these values related to them. We're just saying we identify these images to have a label of a number. It's not necessarily, it doesn't have the value of the number. It's just a way that we mark it. It could be just as easy A, B, C, D, E, if that's what we call these, numbers. So in this case, it's categorical, and that's why we want classification. And then do we want to use regression, neural networks, some kind of model? That's up for you to decide. It comes with experience. It comes with, just some of this analysis. I did some basic logistic regression. This is one of the easier ones to understand. And it's a little basic, so it doesn't actually have too much, it's not like as accurate as it could be. So from sklearn linear model, I import it. You treat it like it's an object, so you just instantiate it right here. And then it's as simple as fitting it for the training inputs to the training labels. And then you can print your score right there using the testing label. So if we run this right here, don't worry about this warning. It's saying it doesn't converge. It's because the model isn't the best choice. But we see that it's around 95% accurate. In case of regression, it's actually going to be consistent, 95%, because it doesn't really have any random elements to the model itself or the algorithm itself. But as you can see, we have 95% accuracy, which is okay. I didn't actually put any parameters. There's a lot of different parameters you can put, penalty, dual, toll, C, fit, intercept. I'm not going to go into detail of what all these mean. You can read what it means in the documents, and I suggest you read it on your own and kind of learn a bit and play with it and see if you can do better. Here, this is just going to be showing some of the wrong predictions. So, you can individually predict values. So this is predicting all the test values. And then I'm just saying, if the prediction misses, essentially, show what it missed. So if we run this right here, you'll see that it says this was a 3. It says this was a 9. It says this was an 8, and then said this was a 2. I mean, I don't know about you, but it's kind of hard to see for me. I mean, I could see, you saying this is a 2. To keep it simple. And so that's something you can think during your data science portion. Of course, we're talking about just the machine learning right now, but you always want to think about your inputs. Would increasing the pixel size make it easier and more accurate? What other things can I add? What other kind of inputs can I do to make it more accurate? What's important for my model? So right here, I'm also going to individually put a single input and see what it predicts it as. So I manually just made an input, 15s all around and zeros in the middle. This is just going to be a solid white outline. And then I'm going to show you what that looks like, and I'll show you the prediction it gives. So if we enter it right here, the reason it's a color right here is because normally I put a color map to make it black and white or gray. In this case, I didn't because it looks kind of weird against the background, but imagine the yellow is white and then the dark is still black. So it'd just be like a single square. I guess you can say this is like a 0 maybe, but as you can say, even the model's kind of confused because it probably doesn't really consider the outer rim that important. And however it's calculating the labels, it's saying, okay, I don't know what this classification is. It kind of guesses, you know. That's kind of the basics of scikit-learn. As you can see, it's actually really easy, especially if we just use the default models, and it's really nice to play around with it. Let's see if we can get a little bit more accurate. I'm going to this time use neural networks. So from sklearn.neural network, I want to import, I'll do MLP classifier. That stands for multi-layer perceptron classifier. Remember, a perceptron is just another name for a neuron, and multi-layer is just saying, you know, it's going to have an input and output and then some hidden layers in between. Again, I'm just do the default. I want to keep it easy because we're not really talking about the actual math and all the detailed theory behind machine learning. I just want to show you how important just the models themselves can be. So we do that, and then we'll do the same thing where we fit it, you know, to our training data, to our training labels. Excuse me, and then I'll print the score. So I'll do MLP score X test to Y test. So if we run this, takes a little bit, and you can see we actually have almost 97% accuracy. So it's a little bit better than our logistic regression. And generally, neural networks are able to add nonlinearity automatically into their calculations, which is what the hidden layers do with the activation functions. You can read a bit more about that in the parameters where you'll see it's different learning rates, and there's different solvers and different activation. Default's ReLU. I would recommend looking at all of these. It's very cool. It's very interesting. And the theory behind it's very cool. And it's going to help you actually get a better score than what I'm getting right now. So right here, I got 96.8%. We can run that a couple more times and see if we can get a different score. The best I've seen is 98 on the dot. And the reason why it's different every time, as opposed to just regression, is that the way that neural networks work is it gives some random initializations, and then it starts optimizing it based on those. So since it has different starting points, it's going to reach different scores each time, or generally different scores. You can see we're kind of repeating scores, but it is different from run to run. And there we go. That's the 98% I'm looking for. So my challenge to you is you'll have everything here besides this little last part. I want to know if you can get a better score than what I got here. So my high scores were 95% and 98%. Of course, I just use the default models. Either you can get a higher score by, you know, changing the inputs, or you can change, you know, these are all the supervised learning models. You can look at all these and try to find different classification models that might work better. Or you can even just change the parameters of the models that I already used. If you go to the GitHub and you want to submit us, you know, branch off and submit your changes, we'll add it to the best scores. Right now, both my names on top because I'm the only one that's actually participated. So we have it right here. We'll edit the README and you can participate alongside. Good luck. And that's pretty much the basics of scikit-learn. So I'll hand the controls back to Ray.
So this basically concludes the machine learning Meet the Models workshop, and I'd like to thank Tyler for providing a great demo on how you can use scikit-learn and their pre-built models in order to tinker around and learn some more on your own about machine learning. And one thing I'd like to remind you all before we go is that we have the DSC Solution Challenge info session on December 7th. So what the DSC Solution Challenge is you have a team and then you try to create a project that helps the local community. And this will be done in the spring 2021 for the UF chapter. And the winner will be recognized by Google and can also demo their application in front of Google representatives. Be sure to join our socials and follow our DSC chapter page. And don't forget to fill out the Google survey form posted in the chat so you can give us feedback on what we can do to improve and what type of workshops you need. Thank you, guys.
Thank you, everyone. If anyone has any questions, we can stick around for a little bit longer because this was slated to go to 8. So if you're curious about anything, we can try to do our best to answer it. Otherwise, I mean, as always, you've been free to go as long as you want. But